So in this video, we're going to start talking about our next ADT, the queue. And again, you've seen the queue before in 143, but we want to kind of revisit this, dive in a little bit deeper, and talk about some ways to actually implement it with the data structure. So you can think of the queue as kind of a fraternal twin of the stack. They're very similar, but slightly different. A queue is an ADT representing an ordered sequence of elements whose elements can be only added from one end and removed from the other. Sometimes we call this a first in, first out structure or a FIFO structure. And similar to the stack, the elements are stored in the order of insertion, but and we don't think about them having indices. So that you can't access the thing at index 2. It only provides access to things at index, or not index, it provides things at the front and the back. That's it. So you remove from the front and you add to the back, just like a queue, like when you get in line at the store or something. And we only let the clients examine and remove things from the front. So we have similar operations. We have add, that adds at the end, remove, that removes from the front, peek, that just looks at the element at the front, etc. So that's the queue ADT. So let's think about how to implement this queue ADT let's start with linked nodes, or with the linked list. So unlike our implementation using linked nodes for the list ADT, we're going to make our implementation for the queue slightly more complex. We're going to allow having both a front pointer and a back pointer, as well as a size. We're going to keep track of the front of the list and the end of the list to make sure all our operations are efficient. Now you might say, well, why didn't we do this with the list ADT? That back pointer would have really been helpful. And the reason was we wanted to have a better comparison between array list and linked list, and keeping it simple with only having one field to keep track of is a very good way of doing that. It's totally valid for your linked list implementation to have a front field and a back field. It actually makes some of the operations quite faster, but a lot of those takeaways we had when comparing array list with linked list that were true for the linked list with just a front, they're still somewhat similar to the case where there's a front and a back. The edge cases just tend to be a little bit different than just adding at the end. But not about that. We have 2 pointers now. We're happy. So how is this going to work with the linked queue? Very similar with the linked stack. We're going to keep track of the front of the list. We just also have that pointer pointing at the end, so we have fast access there. So whenever you add at the end. You probably are going to need, if you're writing code for this, have a special case for if the list is empty, because you need to also update front in that case. But you're going to have back point to this thing. Then when you add 8, you're going to add it because it's a queue. Things get added to the end of the queue, so you're going to add it after the 5. When you remove, you always remove from the front of the queue, so you're going to update front to point to the next thing. And so it's just going to be a queue, just like our conceptual understanding of that. So let's think through what these big O runtimes are. So for the remove, it's going to be constant. Why? Well, you just change a couple pointers. Change the front to point to the next thing. The constant time, you don't have to loop over the whole list of numbers. Peek, similarly, it's constant. You just look at what's at front. Size and is empty. These are usually constant because we have that size field. And now think about add. What would the runtime of add be? This one's also going to be constant because we have a reference to the back. If we were back in Friday's world, where we had the linked list with one front field, then add would have to be expensive because you'd have to traverse to the end. But since we're keeping a reference to the node in the back, it's really easy for us to just say, oh, set its dot next to a new node, and then change a couple more that change the back pointer to point there. So this can also be constant. So linked lists for queues are really good implementations because all of the operations are constant time. Again, assuming you have this back point. So this is great. Well, let's compare this to an implementation using an array. So let's think about implementing a queue with an array and see how that will go. We're going to implement this similar to array list for the list ADT, where we're going to store our numbers in an array that's a bit roomier than before. We're going to keep the things at the front at index 0 and then add things afterwards. So when you add the number 5, you're going to put 5 at index 0. When you add the number 8, you put 8 at index 1. It's just like with the array list. We're just adding at the next available spot in our roomy array. And now when you remove, or sorry, one more add. When you add one more number, you add it there. And now when you remove from the front. And since we want the thing at index 0 to be the front of the queue, we're going to have to shift everything over. Okay, well, now that we have that picture in our mind, this is just like array list, but we're going to use it for a queue. Let's think about the runtimes for these, the big O analysis for these runtimes. Peak is going to be constant. Why? Well, because the front of the queue is at index 0. We can instantly access index 0. It's going to be constant time. Size and is empty are constant like normal because we have that size field. And then the question is, what is add going to be? How can we analyze add and remove? What is the worst possible runtime for add and remove? Take 1 second and try to think through that and answer it. Okay, so what did you get? Hopefully, you're able to figure out that for add, it's very similar to the case with array list, where it's O of n when you have to resize. I guess I didn't explicitly mention that, but it was in the slide. Just like array list, if we run out of room, we're going to have to do a resize, make a bigger array, and copy that over. But most of the time, it's going to be O of 1. So it's kind of this dual thing here, where O of n and O of 1 kind of at the same time. What about remove? Well, remove is going to end up being O of n as well because we have to shift everything. It's just like we're moving from the front of an array list. So both remove is a bad operation for this data structure because it's O of n. It's not quick like the linked list one. And add is bad sometimes. And so it seems like this way of representing this data structure with the front of the queue at 0 is not really working for us. It's making it slow for both add and remove. It seems just like a strictly worse choice. And the reason this is slowing down, the reason this data structure is going to be slow, is because we're using the wrong invariant here. So an invariant is a property of a data structure that is always true between operations. It's true whenever you finish one of your operations, like add or remove, and so you should be able to count on it being true when you start a next one. You're used to invariants. You might just not have used that word. Think back to almost any class you've implemented in your life. For example, if you took CSE 143 here, our first programming assignment was that letter inventory. And in letter inventory, you had a field that was an array, and your constructor initialized it to an array of ints that you can count. Now, in the rest of your methods, you never had to check to make sure that that field wasn't null, because you had an invariant that you set it up in the constructor before everything, and none of your methods would ever make it null, and so you would never need to check if it was null. The invariant there was that your field was never null, and because you never messed up that invariant, you could just assume it's true. You never had to make checks for it. We can also use this idea of invariance when thinking about how we organize our data in a data structure. So our array queue that we just thought of has the exact same invariance as an array list. We basically just redescribed how to use an array list, and I'm using it in a queue context where we just remove from the front. What invariance does an array list have for its data array? So what do we always know is true about the array of data in array list? One thing we know is true is that the ith item in the list is stored in data of I, stored in the ith index of the array. That's a mapping that we made intentionally. Now, this invariant is what slows down us using the array structure for the queue operation, because we want the front essentially to be at index 0. So the remove operation has to shift everything over. And so keeping the same invariant in this other context slows us down a lot. So the question then is there a different invariant we can use? Can we represent this data in an array differently so we don't have to have this big slowdown for both adding and removing? And so the big idea is we can, if we're really clever with how we think about storing data in the array. Here's the big idea. We're going to create what we might call a circular array, where we keep track of both a front and a back, and let the start of the array be front and the end of the array be back. And we're going to use those to let us control what data is in our queue. That's all very abstract. It probably doesn't make sense. It makes sense when I walk through this example. So right now, the state of my queue is 592. 5 is at the front, so it's the first number. Then there's 9, and then there's 2 at the back. There's 3 items in total. When I go add a new number, add number 7, I add it at the back of the queue. So I'm going to go to where the back index is and add it 1 to the right and increase the back index. So now my queue is 5927. Now when I add number 4, you would see that I don't have any room behind me in this array. I'm at the last index. So what we're going to allow, and why I call this a circular array, is we're going to allow back to circle around to the start of the large array. So now back is in front of front, but we always read this starting at front, then going to back. The new trick here is that we allow us to run off the end and start off at the beginning like a circle. So now the state of the queue is 5, 9, 2, 7, 4. 4 is the last number. Okay? Very tricky, but really cool. And so now when I go add a new number, when I add the number 1, now is the case where we've run out of space, and now we need to do a resize. And so I'll resize into a bigger array. I might as well start front off at 0 here, now that I get to copy everything over. There's no need for me to keep it in this circular position, but now we can continue like we left off. So now when I increase back, when I add 1, I can increase back and put it there. And you might be thinking right now, what is the point of this? This just seems like extra complexity on top of what we already had. Does this solve our problem? It doesn't necessarily solve the add problem. Add is still fast most of the time. It's constant work most of the time. But every once in a while, we need to do this resize, which is slow. But the front, now when we want to remove something, well, we could just move front over. Because we've gotten rid of the invariant that the front of the queue has to be at index 0. We're saying the front of the queue needs to be at index front, whatever we're storing in that variable. And so now we could just move that over. And so here is our better implementation of a queue with an array, where it doesn't just keep track of data and size, but it keeps track of front and back. And it does this circular array trick where it keeps track of the queue between front and back, allowing back to wrap around to the beginning of the array. And I kind of already alluded to this when thinking about, well, what's the runtime of these things? Peak is going to be constant time because you could just look at index front. Size is empty are still constant. Add is still linear if you have to resize, and still O of 1 if you don't, which it's the O of 1 case is going to be most of the time. But again, we have this dual case here. But then remove is going to be constant because we just have to update the front. So very, very clever implementation of this.